Okay, thank you very much for your invitation to present you some experimental results we have obtained not on pipe flows, but on a von Karman flow. I'm sorry for that, but it's a very small pipe, in fact, in a cylinder like this. We have obtained this result with, in collaboration with Arnaud Chifaudel, Bérangère Dubrul, Louis Marié, Florent Ravelet, and Pierre Cortet. And I will also speak a little bit about results we obtained not in water, but in liquid sodium, which have been obtained with the VKS team. So what is a von Karman flow for me? This is the flow in a cylinder between two counter-rotating propellers, like this one you see with curved blades, so you have two senses of rotation. And because you are rotating, you have this azimuthal shear here in blue in one direction and in the other direction, and also you have pumping in the center and going like this in red for the poloidal flow. And this flow is axisymmetric in a statistical sense, and also you have an R-pi symmetry against any axis perpendicular to the flow. Okay, so we have performed some velocity and some torque measurements in these experiments. And what do you find? In fact, depending on the observation time, you can get some kind of three scales. First one, when you get an instantaneous shot, what you see is all this mess of turbulence. And then if you do an observation a little longer, what you get is these vortices in the shear layer between the two cells. And if you do the mean on about 1 minute, you get your azimuthal flow like this, and the poloidal flow going pumping in the center and coming back on the edge like this. This is obtained by stereoscopic PIV measurements. Okay, what are the first bifurcations and symmetry breakings you can observe in the flow? First, for very small Reynolds number, what you get is a perfect symmetric and stationary flow. And then when you increase your Reynolds number, what you get is a m equal 2 mode. Again, stationary. This is in the tangent plane of the cylinder. This is in the meridional plane. And when you increase again your Reynolds number around a Reynolds number of 400, you get m equal 2 flow, which is now periodic. You can look at that on the Fourier spectra. What you see is a beautiful peak like this when it is periodic. And then if you increase again your Reynolds number, you have a quasi-periodic system like this with this peak here and a peak here. And if you increase again, you end up with a chaotic flow like this. You still increase your Reynolds number. Now you have this -1 power law on your spectrum, on your temporal spectrum, but the flow is still not turbulent. You see, this is the -5/3 law. And if you increase around 4,000, you get nearly this turbulent slope, Kolmogorov slope. But be aware that you have this bimodal distribution because you are when you make you perform the measurement in the shear layer, you have the two possibilities, minus 0.5 or plus 0.5 for the azimuthal velocity. So this is not a Gaussian. Sorry. So you can also look at all these transitions by looking at the azimuthal kinetic energy fluctuation. And on this graph, I have put this parameter as a function of the Reynolds number. And what you get is a continuous line, which is increasing until you get turbulent around this Reynolds number 3,300. And you can even plot this as a function of the Reynolds number minus a critical Reynolds number to the power 1/2 and see that this is not so bad. So you have a kind of globally supercritical transition with this order parameter, I don't know why, which is going like this very, very nicely. And then you become turbulent with a fully developed turbulence. What you can do also is that you can measure the torque in your experiment. We have done that from a Reynolds number from 10 to 1 million by doing a different mixture of glycerol and water. And we have measured the torque. This is the reduced torque, which name is Kp, as a function of the Reynolds number. What you see is when you are not turbulent, you have this -1 law, which was expected and which was seen which was observed in other different experiments. And then once you are turbulent, you have this curve going like this. And what you see is that your torque is depending on the sense of rotation first. This is the blue and the red curves. But also that for the same Reynolds number, around 10,000, you can get a multiplicity of solutions. And this is a great difference because you have a factor 3 between the two possible solutions for the mean flow, even if you are already fully turbulent. What happens, in fact? These are velocity fields obtained for a Reynolds number around 300,000. What you see is that your perfect symmetric velocity field, here is the torque as a function of time. This corresponds to the symmetric field with two cells, can suddenly change to a one-cell feature like this one with a very different torque. This is a factor 3 between the two. This is not a small effect. This is a very large effect. And this transition is obtained on a fully turbulent flow. So you have a symmetry breaking between the two flows. You can look at this reduced torque, and in fact, I can define an order parameter. That is the difference between the two torque of my two propellers. And what you see is that you have this symmetric cell, symmetric state with the two cells only for a difference of frequency between the two propellers. Theta is the difference of frequency between the two propellers, F2 minus F1, only for theta equal to 0. As soon as you increase or decrease your theta by just a little bit, you end up with a one-cell non-symmetric state, and then you stay on this branch. And you have a very strong, very large hysteresis loop like this one. And once you are on this non-symmetric state, you can never go again to this symmetric state. You have to stop your experiment and restart again your experiment to get this symmetric state. Now what you can do is that you can study the stability of the symmetric state. You can perform some statistics on a lot of runs for a lot of different theta. And what you see is that this time you have to wait for the bifurcation. It behaves like an exponential, defining some characteristic bifurcation time. And this characteristic bifurcation time here is evolving on 1, 2, 3, 4 orders of magnitude as a function of your theta. Theta, I recall you, is the frequency difference between the two propellers. So this means that the symmetric state is marginally stable. That means that this characteristic time is going to infinity when theta is going to 0. But what was very strange for us, for experimentalists, is that the exponent is -6. This is very unusual in this kind of experiment. Okay. I told you that we have multistability, and that this multistability is a function of the Reynolds number. We have no multistability under Reynolds number 10,000. You can look at that on this diagram. This is the torque difference between the two propellers as a function of theta. What you see is that for Reynolds number 800, for example, in black, you have a continuous line, and then you increase your Reynolds number in blue, 5,000, you get a small jump, but you still can go through the symmetric state. But above 10,000, you have this hysteresis, which becomes to grow, and then you end up with the graph I showed you before for a larger Reynolds number. So this this transition, this turbulent bifurcation is a function of the Reynolds number. Okay, I told you that there is, when we are doing some velocity regulation, there is this forbidden zone here. I can go to the symmetric state or to the bifurcated state. But what I can do is that, as I'm using electrical motors, I can perform some torque regulation instead of velocity regulation. And in that case, I can go in this forbidden zone, and I can get this symmetric state on a, on a larger range of delta Kp. And also, I can get some intermittent states, meaning regimes in which you are going from a one-cell state to a two-cell state a long time with a very slow dynamics. I can show you this dynamics. So this is torque regulation, and you have this stochastic transition between a one-cell state and a two-cell state. This is for very different torques. So we know that for very different torques, we have this one-cell state only. This is theta in red, and this is the average frequency in blue. So we are imposing the torque, and we are measuring the frequency of rotation, okay? So now, if you go closer, if your two torques are going closer, what you see is these intermittent behaviors between the two states. The lower states correspond to the one-cell states, and the upper states to the to the two-cell states, okay? And then, when the two torques are nearly equal, you end up with your symmetric state with your two cells like this. So you have this transition by changing the torque. Okay. Now I want to show you a slightly different experiment. This is also a von Karman flow, but this experiment was designed to observe a dynamo action in a conducting fluid. And for that purpose, we use slightly different propellers with a reduced curvature. And also, we put a small annulus here in the shear layer, because we wanted to try to influence, to stabilize this shear layer and the vortices of the shear layer here. You can see on this picture the small annulus here and the propeller at the back. We performed the same experiment first in water, and what do we see? First, without annulus, we see a transition. This is the position of the separatrix between the cells above and under. Here is one propeller, here is the other propeller. And in this case, with this kind of propeller, there is a continuous transition like this, without annulus. Now, if we put this small annulus here, in the middle shear layer, what we see is also we have this jump like this. And in fact, we can draw the same diagram I showed you before. This is a delta Kp. This is the difference between the two, the two reduced torque in the experiment. So you see there is a small transition here, but a very small hysteresis and a very small Kp difference. And it happens to be quasi-continuous. This is very different from the other transition I showed you before with different propellers. But in this experiment, what do we get? We get that when we perform very long acquisitions around this transition, we see that we are going from the symmetric state with two cells towards the bifurcated state with one cell. This transition is quasi-continuous, and this is going through very slow dynamics. This is the transition between symmetric, bifurcated, symmetric, etc., bifurcated state as a function of time. But in this case, we are doing velocity regulation and not torque regulation. And this is this is going between the two states. You see on very long time, this is 6,000 seconds. We don't know why we have this very long times. So this is the complete curve to see the transition around for CT, some critical theta around 0.175 here. This is the symmetric state here, and this is the bifurcated one-cell state here. And why I wanted to show you that is that you can also look, you can perform some statistics and look at the probability of presence of the symmetric states. This is 1 before the transition, this is 0 after the transition, and in red, this is the probability presence of the bifurcated state. And you see that the exchange stability around this. You can even plot the ratio of the two probability of presence of your two states. You will see tomorrow a talk by Javier Burguete also on this subject and on the slow dynamics obtained in the, in the same geometry, but with a quasi-perfect axis symmetry. And why I wanted to tell you about this slow dynamics is that because in the von Karman now, but with sodium instead of water, what do we see? First of all, we can see the generation of a magnetic field. And second, depending on the rotation of the two propellers, for difference of rotation of the two propellers around this critical theta, what we see is these erratic reversals of the magnetic field. This is the magnetic field as a function of the time. And what we see is this very slow dynamics, which seems to be very reminiscent of this dynamic I showed you before on the hydrodynamic state. So to conclude, I wanted to ask the theoreticians here, who are here, what do we see, why do we see bifurcation on turbulent flows? You can have this, the turbulent bifurcation I present you on the von Karman water flow. You can see also these magnetic field reversals in the von Karman sodium flows. And I recall you these turbulent stripes we have observed with Arnaud Prigent and Olivier Dauchot in the plane quad flow. And also the turbulent spirals, which have been observed by Arnaud Prigent and Olivier Dauchot in the Taylor cruet. All these things are remains of bifurcation in fully turbulent flows, and I think we have to understand that and to have some theory about that. Okay, thank you very much.
You have showed that the first bifurcation from the laminar flow
yes.
Was square root dependence on the
yes.
distance from the Reynolds number
yes.
or the kinetic energy.
Yes, of the azimuthal component.
For square
yes,
velocity
yes.
and not for the velocity.
Yes.
This is very unusual. Could you comment on that?
No. This is an experimental result. That's what I can say. I know this is very unusual, but
it's possible to fit it with a square for the velocity and not.
No, it's not. It's not. Definitely, it's not.
Because this implies that in your Wickli nonlinear theory, there would be no quadratic term in amplitude, and I don't see why this should be.
I don't know. It's just an experimental observation.
It is with theta squared. If you would RMS, if you would plot other velocity RMS,
yes.
Would it be also like this, or would be?
It's slightly different, but
different.
Yes, a little bit, but
Okay,
it's not. It's not.
Will you have square root in other RMS?
No.
But not.
It's near this curve.
Okay.
Now you have to go all the way to the end. The magnetic field reversal events show an asymmetry through the transition. Do you see that in your strictly hydrodynamic?
I think the asymmetry is due to some magnetization of the experiments, a little magnetization. There is no, in fact, depending on the fact that the magnetic field you have generated is going in one direction or the other direction, you get this slight asymmetry. But we have not observed the same in hydrodynamic plot. This is not related, I think.
Okay, thank you very much.